Hey everyone, I hope you all are doing good. So in this lecture, we're going to be looking at two very interesting applications of recurrence, right? Uh, just like I covered in the last few lectures, right? Like what the purpose of recurrence is basically that um, whenever we are trying to solve a problem, in a lot of the cases, the first thing or the first solution that it comes down to is recurrence. And after recurrence is solved, then we try to figure out some other solution. And the problem is, um, recurrence is the first way that you can try to figure out the solution to a problem. But the thing is that, let's say if I'm trying to find some value, let's say A999 in a recurrence relation, uh, the problem is I would have to find A998, A999, sorry, A997, and keep going back again and again multiple times, right? So what we do is we try to first find a recurrence relation because that's the only way possible. And then once we have the recurrence relation, then we try to find a simpler formula so that we just have to input one value and we don't have to use the recurrence. Okay, so Tower of Hanoi is one of the very important examples in computer science, and we will cover one more example after this. One more thing that I wanted to discuss is that I've been working on some animations for my lectures, and I'll be uploading them as short form content on YouTube. So you guys can watch like those animations and let me know if you guys have any feedback on these animations, right? So for Tower of Hanoi as well, I'll be giving an animation explanation for it in this video, and then we will move on to the next topic, right? Okay, so Tower of Hanoi is pretty much you have three pegs A, B, C with n disks. On peg A, stack largest to smallest, right? So it's pretty much you've been given these three pegs, right? Your entire task is to move all these three pegs from A to C. But the important goal is that um, you can only move one at a time. So that's one rule. And the second is a larger disk cannot be put on a smaller disk. So it's not like I can just put the smaller one here and then the second one on top of it and then move the third one to that third place, right? What I have to do is I just have to move it once at a time, and then I cannot put a bigger one on top of a smaller one. So this is a very interesting problem, and I'll show using animation how to solve it. But this is like a recurrence relation problem, right? So let's just try to see this problem using animation, and then I'll give the formula on the board again. Okay, let's start with three disks. We need to get all of these from A to C. That's our goal. So first we need to move top two out of the way. Smallest disk goes from A to C, disk 2 to B. Now the smallest goes on top. Top two are on B now. Now the biggest disk is free. So there it goes from A to C. That's the key move. Now bring the two disks from B to C. So smallest to A first, then disk 2 to C, and then smallest to C. And that's done. So that's 7 moves in total for 3 disks, which is 2 to the power of 3 minus 1. But what happens when we add another disk? So let's try it with 4 this time. Watch how the same pattern shows up, right? So 4 disks now. Step 1, we need to move the top 3 to peg B. And notice moving these disks, that's the exact same problem we just saw. So watch. It's pretty much the same 7 moves, but rearranged. So top 2 go to the helper peg, then the disk 2 moves, then the top 2 follow. Okay, so now the biggest disk is free, right? There it goes from A to C. That is always the key move. So one single move in the middle. Now we do the n equals 3 problem one more time. Move these 3 disks from B onto C. So same 7 moves again, top 2 to the helper, then disk 2, then top 2 follow. You can see the pattern pretty much. And we are done. So that's 15 moves in total, which is pretty much 2 to the power of 4 minus 1. So for 3 disks, we took 7 moves, and for 4 disks, we needed 15 moves. So 15 equals 7 plus 1 plus 7. Move the top 3, move the biggest, move the top 3 again. So t of n equals 2 multiplied by tn minus 1 plus 1. Now let's see how the recursion actually breaks down. Here's the Hanoi of 3, A to C. It breaks into 3 parts. Move top 2 to B, move the biggest, move the top 2 from B to C. And each of these smaller problems break down the same way. Left side, 3 substeps, right side, the same thing. Now watch how the execution order. Step 1, 2, 3, 4. That's the big move in the middle. and then we have 5, 6, and 7. So those are the exact 7 moves that we just saw earlier. So 7 moves, which is 2 to the power of 3 minus 1. And now let's write it on the board. Okay, so I hope you guys liked the animation and like you were able to understand what I meant by the animation. If you guys have any suggestions for me for the animations, let me know and I'll try to make any changes that I could, right? I've just kept this like to be a retro kind of a style. It's like easy animation for me to make. And I'm gonna also upload like short form content in like the reels so that you guys can like scroll down and then watch all the short form videos of discrete math pretty much. And I'll do the same for like other concepts too. Okay, so I hope you were able to understand from the animation the Tower of Hanoi problem. So it's pretty much, now let's look at the formula of the recurrence, right? So Tn is the number of moves for n disks. We know that T1 would be 1 because let's say if I want to move, I just have one disk and I have 3 pegs, right? So in order for me to move from A to C, I just need one move, right? For Tn, if I need to move n disks, I need to move the Tn minus 1 disks 2 times, right? Because if you looked at the animation, you're pretty much moving it once. You move the one at the very bottom to the final C, and then you need to move all the disks back again to the final one. So it pretty much gives you 2 times n minus 1, 2 times t n minus 1 plus 1. So this is move n minus 1 disks 2 times move final disk from A to C. And that's pretty much it. So I hope you guys were able to understand this problem. Now let's take a look at another very important example or application of recurrence relations. Okay, everyone, let's take a look at a very interesting problem, right? Now, this is the problem that we're going to solve using recurrence once again, just like we solved the Tower of Hanoi problem, right? The idea is have a base case, and for all the other cases, solve one problem and then leave the rest to the previous recurrence part, right? And then this way you could have this entire sequence, or I should say like a chain being formed where it relies on the base case, right? Okay, so the question is, how many bit strings of length n have no two consecutive zeros? What do we mean by no two consecutive zeros? So let's say for a bit string of length n equal 1, you could have 0 or 1, right? So these are valid bit strings. Why? Because they don't have any consecutive zeros. And they've also mentioned an is the number of valid bit strings of length n. Valid in this case basically means that there is no two consecutive zeros, right? So for n equal 1, you could have 0 or 1. So A1 would be 2, meaning A1, you could have 2 valid bit strings or 2 strings where there are no consecutive zeros. For n equal 2, you could have 1, 1, 0, 1, 1, 0, right? You cannot have 0, 0 in this case, right? Why? Because 0, 0 is not a valid bit string because 2 zeros are consecutive, right? So for the case of n equal 2, you would have A2 equal 3. For n equal 3, you could have 1, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, and then you could also have 0, 1, 0. So A3 would be 5. Okay, so this is just me trying to explain the problem to you guys. I hope this is kind of making sense. So for n equal 1, meaning if for the length of 1, you could either have a 0 or you could have 1, right? So the number of valid bit strings would be A1 equal 2. For n equal 2, A2 would be 3. For n equal 3, it would be 5. Now the problem is we need to find it for the length n, and we need to find the formula for some an, right? And I cannot just keep on solving this problem, so let's just try to figure out how would we do it. Okay, so once again, we're going to use recurrence to our advantage. Okay. First of all, let's talk about the base case, right? Because in recurrence, we need the base case. For a bit string of length 1, we already know that this would be 2, right? So if the length is 1, you could either have 0 or 1. Okay. Another case would be for A2. Let's just print out a few values, right? For A2, we had 3 possible valid bit strings, and A3 was actually equal to 5. Okay. So now I'm going to use the recursion to try to solve this problem. Let's just first see for a valid bit string of length n. Okay. For a valid bit string of length n, let's just divide this problem into two parts first, right? One, it ends with 0, right? If I have a valid bit string of length n, it could either end with a 0. Second is, it ends with 1. I think this will make more sense when I try to like bring this further down. But the idea is very simple. For any term, I'm trying to bring it down further back until I reach the base case. That's how recurrence works, right? So for example, you would have a formula like an equal an minus 1 plus 1. So meaning it depends on the previous term. And that's exactly what we are trying to do in this case, right? We are trying to go back a step and trying to rely back on the previous person that we had. So let's say if it ends with a 0, what should we do? So let's say you have multiple terms. If it ends with a 0, right? Let's just, if it ends with a 0, then how many, like what is the number of bit strings that you can replace with, right? If it ends with a 1, how many bit strings can you replace with? Try to pause the video and then try to figure out like any sort of idea you guys have, right? Okay, so let me just try to explain the example of 1 first, right? When the bit string ends with a 1. Okay, so if a bit string ends with a 1, if I'm using recurrence, how about I can just replace the previous terms with an minus 1? So if my bit string ends with a 1, right? For my previous terms, I would have an minus 1 choices, right? Why? Because think about this, right? For a value ending with 1, I could have 1 0 0 1 1 1 1 0 0 1 1, anything, right? I could have any combination as long as that combination is where 0 is not being consecutive. So how about I just take a step back and then I go back to the next person, right? Or the previous person I had. So let's say, okay, this bit string ends with a 1. I can give it to the previous person behind me, and then I can tell them that, okay, you already have the count of the bit strings of length an minus 1, right? Yeah, that's all we need. You can replace this many values with that amount. Okay. Now, for the case where the bit strings end with a 0, right? I cannot have an minus 1 values. Why? Because think about this. For an example of, let's say you have a 0 and then you try to replace it with an minus 1. What is an minus 1 again? It is the number of valid bit strings of length n. But if I replace this with an minus 1, I could replace it with a 110. Now 110 is a 3-digit valid bit string, but when combined with the final 0, right, it becomes false. So what I would have to do is, in the case I have 0 as my final bit string, I need to first replace the second last with 1. So I would have n minus 2 remaining values, and the n minus 2 remaining values could be an minus 2, right? And that would be the final answer. So just a quick summary once again, right? For a valid bit string of length n, I'm trying to use recursion to my advantage. Okay? I'm saying it could end with a 0, right? In the case it ends with a 0, right? I'm trying to find an, right? If it ends with a 0, then I would have to replace the second one with a 1, and then I can just leave everything else back to the previous recurrence relation, right? Meaning I can replace it with an minus 2. So an would be an minus 2 in case the final value is 1. Plus, I also need to add when the final value is 1. So if the final value is 1, I can replace it with an minus 1. And that would be your final answer. And if you guys remember, this is basically the Fibonacci sequence. Okay, so I hope you were able to understand this lecture, and I'll see you guys in the next video.